Okay, so there's a lecture today. We may not get through it all because there's a lot of other things I need to talk about. I guess first things first. So the Gauss-Seidel project, this is what I wanted. I have updated the PDF for it. A couple of you have submitted it already. I put a due date on here for you, Robbie, so there you go. And I made the picture bigger for you. And then what to turn in, I haven't been very explicit on what I'm looking for. It's caused some confusion. So I tried to spell it out a little bit more, in a little bit more detail. You want a tarball containing a report of your results and then your source code. For the strong scaling, I want a figure of the measured speed up for n equals 100, 250, 500. This is the number of nodes. I want you to compare your measured results against Amdahl's law and also the ideal speed up, which is a 1-to-1. So you should have a nice 45-degree line on your plot. I want you to estimate and report the serial fraction for each value of n. Okay, for the weak scaling, do the same thing with starting at n equals 100 for one processor, and then compare your measured results against Gustafson's law and the ideal speedup, estimate, and report your serial fraction. All right. Write a short paragraph presenting your results. And what I mean by this is if you have a figure, you should write something about it. Okay?
Sounds about right.
You just throw it in there?
And then, does the red-black scheme scale better or worse than your Jacobi? And why do you think this is? Little hint has something to do with work and the amount of work that is done. Anyway, so also want to make file in there that will compile the code and then make run, which will run the strong scaling study at n equals 100 from 1 to 4 processors. Okay, so I've updated that. That is due tomorrow. I'm going to go over a little bit more today how that is to go, or how to actually do the red-black scheme. Okay, so let's see here. Was there anything else? Let me see. What did I write down here? Okay, so talking about red-black still. Here is my handy-dandy notepad. So here we have our red and black nodes. Notice I've got my I and my J. I was a little lax and freewheeling in how I explained this, and it caused more confusion than it helped. So this is what I explained to you in the previous lecture. You're going to have two loop bodies. One is for the red nodes, one is for the black nodes, and I've got those here and here. And I said the red node starts at I equals 0, and we're going to jump by 2's. However, and then we do the same thing for J. However, if we actually follow this, what we get is this node, and then we jump by 2 in the, so that's jumping by 2 in the J direction. And if we jump by 2 in the I direction, we're going to get these two nodes. But you'll see now we're missing these guys here. We haven't covered those. So one way to fix that, you can add a second loop body that starts at I equal to 1 and J equal to 1. okay, which would start here and jump by 2 to get those nodes. Okay, so that is an option. However, there is a slightly more elegant option. Wow, okay. I need you to clean up my screen. Okay. And the slightly more elegant option works like this. So on the I index, we are going to increment the I index by 1 instead of 2. And then we're going to add a new variable, and I'm just going to call it JS for JStart. And that is going to be equal to I mod 2. If you're not familiar with the modulus operator, what it does is it gives you the remainder. If we divide I by 2, instead of giving us the result of the division, it gives us the remainder of that result. You go all the way back to like second grade math. When we did remainders, that's what it gives you. And so this actually works out quite nicely, because if I is equal to 0, you divide that by 2, the remainder is 0, which starts at the bottom corner node. And then we're going to jump by 2 from there. If I is equal to 1, if I is odd, then that's going to give us a remainder of 1, which then tells us to start here. Okay? And so we can set J equal to JS like that. And now we can cover all of the red nodes in the domain. Okay? So if I is even, we get 0, which starts us here. If I is odd, it gives us 1, which starts here. Okay, and I'm going to leave it as an exercise for everyone else to figure out how to do the black loop. Okay, but that is an option there. All right, so I hope that covers, I hope that helps everyone's understanding with the red-black. I have had some people finish this, so it's not too bad, I promise. Now, something else I want to cover. A lot of people were having problems because their code was taking a really long time to run. And I looked through a lot of code and couldn't figure out why it wasn't working, or we fixed a lot of problems and it still wasn't working. Finally, it boiled down to this. When you compile a program, that is an O, as in capital O, you must have this flag if you want it to go fast. Okay? I mean, if you want your code to run like it was built in the 1950s, you can throw it out. But we don't want that. Okay? So, anyway, you definitely need this. So this is the optimization flag. Now G++, if you do a man G++, let's see here, let's take a look. Alrighty, here is all of the possible flags that you can give G++. And then here is all of their explanations. As you can tell, we don't really want to have to go through all this documentation. Now, a lot of these flags deal with optimizations. Things like loop unrolling, things like inlining, and a billion others that I don't even know. I mean, there's lots of other people that don't want to do this. So they provide what they call the -O flag. And this is the optimization flag. And you can set different optimization levels. Okay, there is the O0, that's the default, no optimizations. O1 does a few, O3, or 2, sorry, does a few more, and O3 is the most aggressive. It basically turns on everything it possibly can. It is possible, I've heard it's possible for O2 to actually generate faster code than O3 because O3 gets ahead of itself. But that's something that you'd have to test for yourself. I just generally just throw an O3 in there and be happy. There is also, I think there's an OS, which optimizes for program size. You don't have to worry about that because we're not dealing with embedded hardware. And then there is the, I think it's OFast, which is like one step above O3, but it could break your code. So these ones here are guaranteed to, they're supposedly guaranteed to not break your code, not give you incorrect results. This one could give you incorrect results. I don't even know if that's a real flag. It's like fast math or something. Anyway, just so everyone knows, do that. Otherwise, your code is not going to go anywhere really fast. So then the other thing I want to talk about is plots. When you're making plots, okay, I haven't required you to write full reports, I know, but when you make plots, you always need to make them correctly. You either need a title or a caption, okay? One of the two. You need an X label, you need a Y label. You need units on these labels. If you have multiple lines, you need a legend detailing what those lines are. Okay? And you need to think about, what is this plot trying to tell? A plot is there to give information. So if we are doing, say, our speed up cases, if you give me, even if you have all this stuff, but you give me 3 plots, one for n equals 100, one for n equals 200, and one for n equals 500, that's not very useful to me because I can't compare them, which is far more useful. You know, if you stick them all on the same plot, then we can say, oh, look, n equals 500 scales better than n equals 100. And so this is what I have been expecting. And I've tried to give individual feedback on that, but there has been some confusion on that. Last but not least, when we are dealing with OpenMP, okay, first off, I guess I never said this explicitly, but if you try and do this, this does not work. I don't know why, but it doesn't work. Your program will hang. It just sits there and does nothing. It only works if you specify, if you hard code a number in there. It will not accept variables. I don't know why it doesn't throw an error. I don't know why it doesn't work. I can't find anything that says it shouldn't work. But the workaround that I found in which I did talk about. Ooh, that's a really wonderful noise. Is this. So we have to turn dynamic threading off. What dynamic threading does is if, for instance, we have two parallel regions, if your program has two parallel regions like this, if dynamic threading is turned on, in which case this would be a 1, and it is on by default. If you spawn, say, 4 threads here, then when it ends this parallel region, it doesn't actually get rid of those 4 threads. It keeps them around just in case it's going to need them again. And so when we enter the next parallel region, even if you say 2, it's got 4 and it's going to use 4. Okay. I'm still a little hazy on why this is or how it works exactly. But the point being, when you so we have to basically, if we want more control, we just have to turn it off. Okay. And in our case, we want more control because we're doing scaling studies. Okay, and we want to say we want 2 threads. But like I said, we can't use a variable. It doesn't work, and I don't know why. But thankfully, they give us a function in which we can say we can set the number of threads.
That's what I did, and it seemed to work. It didn't, though.
So you did what I just said doesn't work? Mm-hmm. Okay, well, for a lot of other people it hasn't worked, and it didn't work for me. I don't know why.
Is that right? Is that what you're saying?
Yeah. That works.
Okay, well, Robbie got it to work apparently.
It worked for me.
Robbie got it to work. I didn't. So I'm telling you the way it worked for me and the way it's worked for everyone else who's had this issue.
Alrighty.
Anyway, after this point, yes, I want that one. Okay. After this point, we can have the parallel region. And because we've already set the number of threads, we don't need to use the num threads clause. Okay. Now, when we are inside of a parallel region, I tried to make this known, but I want to reiterate it because we've run into a lot of problems with this, is that if you have a variable, a shared variable in a parallel region, and you try and write to it, even something as simple as this. This is a data race condition. Okay, if 2 threads try and write to the shared variable at the same time, you could get a 0, you could get a 1, you could get garbage. Even though they're both trying to write zeros, they could clash with each other. And so you have to protect the access to these shared variables using either a critical region or a single region or an atomic construct, which I haven't mentioned before, or a lock, which I have talked about a little bit. Now, Yushi up here thinks this should work.
Well, was just saying, because like, isn't the binary for 0 just all zeros?
All zeros, yes. However, I'm trying to instill good practices in you.
So this one case might work, but it won't work for anything.
It won't work for pretty much anything else, okay? I'm trying to instill good practices in you. If it is shared and you are writing to it, if you are changing its value in any way, you have to protect it somehow. And there's multiple ways to do that. You can use a single, a critical, and that's not how you spell critical. There we go. You could use a master region. You can use the atomic construct, which I haven't talked about. You can use locks, which I have talked about a little bit. You can use, or in like a for loop. Okay, when we're dealing with arrays, those the arrays are shared, but each process is only accessing. There's only one process accessing a particular part of the array at a given moment. Yeah, that was difficult apparently. Okay, so if we do a for loop and we're working with an array, okay, OpenMP sections out the loop, and so each AI is only accessed by one processor at a time. If, however, that is not the case, then you have to be more careful in how you deal with that, either using locks or restructuring your loops somehow. Maybe you can add a second array in there that could be a temporary working space. And generally, the big one. Sorry, I almost forgot. This is the biggest one. Make your variables private, in which case you don't have to worry about it. Okay? Oh yeah, and then there's reductions. Okay, so I think that's everything that I had on my mind. So if you have any questions, again, email me. I did successfully do a Google video chat call the other day, so I'm willing to do that as well. Okay, to the presentation. So today we're going to talk about MPI collective communications, and then if we get to it, non-blocking communications. So everything we've talked about so far has been what they call a point-to-point communication, where we go from point A to point B. We send a message. All right, a collective communication is one that involves all of the processors. So there's one called a broadcast, where we're going to take a value from process 0 and we're going to broadcast it to everyone else. Okay. Important things to know, all collective communications are blocking. Okay. And this means that all processors in a given communicator must call that function. If they don't, the whole thing deadlocks, because they're all waiting for this one guy to show up so they can go to the party. Collective communications are very nice to use, and they tend to be more efficient than you trying to implement the same thing with just sends and receives. So some of the big ones. We have the MPI barrier. This works exactly like an OpenMP barrier. It stops everyone and they all sit there and wait for everyone to show up. Okay? And you have to give it the particular communicator. So in general, it's just going to be MPI, whoops, it's all caps, MPI COM world. Okay, that's generally what you're going to be using. So that one's fairly simple. And in most of the time, you don't need it. Okay? If you do need it, it's usually for debugging purposes, and that's about it. So then we have the MPI broadcast. Now the broadcast takes a few values. We have the buffer, we have the count, the amount of data, the type of the data, the route, and the communicator. So this broadcasts values from the root to everyone else. And the root doesn't have to be 0. Generally it is 0 just because it's 0. It's the beginning. And so anyway, on the root, the buffer, this variable here, this is the data to be sent. For everyone else that's not the root, the buffer is where to put that data. Okay. And the root has to be the same for everyone. If it's not, it'll fail. Okay, you'll deadlock. Because if processor 2 thinks that the root should be, well, himself, and the root actually should be 0, then he's sitting there trying to send out data while everyone else is trying to receive data and the whole thing goes kaput. So that's the broadcast. It's fairly simple. Because we're using pointers, you can send more than one value. You can send an entire array of values. But if you want to send a single value, you have to use the funny ampersand sign. I don't know how to draw one of those things. That's a cursive S.
What's it, the treble clef?
No, the treble clef looks like this.
Oh,
I do know that one. All right, so you do ampersand var, because that gives the address of the variable, and set it to 1. So you're sending one piece of data, one variable. Now, okay, so then here's another one. MPI reduce. This is a global reduction operation. It does exactly the same job as a reduction in OpenMP. Okay, it has a send buffer. It has a receive buffer. The amount of data, type, the operation you want to perform, the root of this collective communication, and then the communicator. So send buff is the data to be sent. All processes are going to have some piece of the puzzle that they're going to send. Receive buff is only used on the root process. Okay, it stores the final values. On all other processes, this could be null, or on the root process, you can also use the special value MPI in place. So it would look something like this. You do a send buff, you send a pointer, and then you do MPI in place. And apparently I run out of room. And then you do your count, and then yada, yada, yada. Okay? And so what that does is it, instead of using a receive buffer, it just reuses the send buffer. Op is the operation to perform. Valid operations are MPI max, which takes the maximum value of everybody. The min, which takes the minimum value of everybody. Sum, which adds everybody's values together. And product, which multiplies everybody's values together. It is possible to create your own. And here's an example here. So MPI reduce, you'd send it my variable. I want to say in place, a count of 1. This is a double. I want to sum it all up. The root is 0. So what this does is it takes values from everyone. So if this is our little world here, we got 3 processors, and everybody has, this guy's got a 2, this guy's got a 3, this guy's got a 4. And this is going to sum all of these together on the root, which I've said to be 0, and so this now gets a 9. Everyone else doesn't know that value, but there are ways around that. So, all right, some other important ones. MPI scatter and MPI gather. Scatter, I feel like, is a little easier to use. But let's say on processor 0, you have an array of values. Okay, and if we have 4 processors, okay, what the scatter does is it's going to take this array and chunk it up into 4 different pieces and say, okay, you go to processor 0, which is me, you go to processor 1, you go to processor 2, and you go to processor 3. Okay, so that is a scatter. You have to have a root. I haven't put it up here because I'm not expecting us to use it for this class, but it is important to note. And an MPI gather does the exact opposite. It takes little pieces from everybody and gathers them all back together at the root. And by default, this sends equal chunks of data from everybody, or to everybody, or from everybody. There are vector variants, which are MPI gather V and MPI scatter V, which takes an unequal amount of data. It takes a little more work on your part to get it to go, but it does the same thing, except now the chunks can be different sizes. Okay?
Are these all blocking?
Yes, all collective communications are blocking.
So what if you have 4 different processors? They all have data that you're supposed to be scattering to everyone and gathering to everyone. Is the best way to just declare a separate variable where you're gathering it all into and then
generally, yeah.
them separately?
Yeah. Oh, I forgot to mention the reduction operation, MPI reduce. This one could come in handy for your Pi program.
So what's, well, I guess never mind.
All right, so then there's the all variants. These do exactly the same thing as MPI gather and MPI reduce, except that all of the processors receive the final result. So my example back here, instead of just process 0 receiving the 9, all of them would get a 9. Okay, if you use the all reduce version. And those don't actually have a root because you're not sending it to a particular process. Okay. So, non-blocking communication. So I talked a lot about the semantics of this, of how it actually goes down, but here we're going to talk about how we actually program it. And so the non-blocking communication, we have an I send. The I stands for immediate. I personally would have preferred an A for asynchronous, but it's about the same thing. And we have the receive. So if you remember, which you probably don't, but if you remember what the send looks like, really the only difference is we now have this right here, this MPI request. It takes a pointer to a request object or struct. The receive also has a request. You'll notice it does not have the MPI status. And so this request object, what it does is it contains information on how the non-blocking message is progressing. And so we can find out information about the message through a few different functions. One is the MPI test, and the other is MPI wait. Now, MPI test has a flag pointer that you have to send it, and it also has our MPI status. So the MPI test, what it does is it tests, is the request complete? If it is, then it sets the flag equal to 1. The request becomes deallocated and is set to this value here of MPI request null. And then status will contain information about the message. If you don't need to know information about the message, you can also use this instead. And then if the message is not complete, it says, okay, so I'm asking, is this message finished? And it says no. Then the flag is set to 0 and it returns. Okay, so it's really fast. The other function is MPI wait. And what this does is it waits until the message handled by request is complete. Okay, this basically says, all right, at this point, I'm going to block. I'm going to wait until either the send or the receive is finished. You can also use the MPI status ignore here if you want.
Doesn't that kind of defeat the purpose of using MPI wait though?
Not necessarily. Because a lot of times, I mean, if you write your program right, you already know how big your message is. And so you don't need to check and see how big it is. They actually have lots of functions. I'm just giving you the major 3 here. Then there's the MPI wait all. There is a test all as well, I believe. But if you have a lot of messages that are outstanding, and if you store them in an array, then you can just say, okay, wait for all the messages to finish. Instead of having to wait for one and wait for another and wait for another, you can just do all of them at once. And you send it an array of requests. You send it the number of messages that you're waiting for. And then you also need an array of statuses. And they line up 1 to 1. So the information for message 1 goes into status 1. And you can also use the MPI statuses ignore. Notice the plural there. Yes, we have grammar in this class. And so that is kind of the basics of how to do the asynchronous communication correctly. If you don't use the test or the wait and you try and modify the buffer before it's sent the message, then you'll get garbage. Remember the parable of Larry. So collective communications are really nice. They can be really handy. They're a lot simpler and easier to use than sends and receives. Sure, why not? All right, so we got 10 more minutes. Now I want to talk about, that didn't take nearly as long as I thought it would. So I hope that made sense. I'm trying to go slower. Okay. I want to talk about arrays in C++ and how we pass them in MPI. And for this, the standard vector is going to be your friend. So let's see here. Okay, this is technically correct, but you get the idea. Now, let's say, for whatever reason, on process 0, we want to send an array of size 10 to process 1. So in this case, here's what I would do. Now, the standard vector is designed to be contiguous in memory. It's supposed to be a replacement for a dynamic array. So a dynamic array would be something like this. However, there's lots of problems with this because you can overrun your memory and you can do all sorts of nasty things. You can forget to delete the memory, in which case you have a memory leak. Anyway, it's just a bad juju. And so they invented the standard vector. And we tell it we want it to be of size 10. And then we do some stuff with it, and then we want to send it. So we use MPI send. Now, the very first argument, if I remember correctly, is a pointer to the data that you want to send. So there's a handy little function called data. And what this does is returns a pointer to the data. And the data is guaranteed to be contiguous in memory. So that's easy. And then you can do that. Get the size. And then we tell it we want to send to process 1, if I remember right, and then we do a tag of 0, and we tell it MPI com world. Okay. So that is by far the easiest way in C++ to send an array of data. On the receiving end, if you know how big your array is to be, then we can do, let me just make a, okay, so on the receiving end, if we know how big it is, we can say, we can use the resize function to make sure we have enough space. And then we just say, there's my buffer. That's where I want you to put the values. And we are receiving from process 0 with a tag of 0 with MPI com world. Okay, does that make sense?
What's the MPI com world doing again?
So that is the communicator. It's the default communicator. It includes all the processors that are involved with this. Okay, if we had another communicator, we could use that instead. But MPI com world is the default. You're not. Actually, we are going to be making our own communicators.
Yeah, MPI com world just has like all the processors on it.
So basically what it's saying, I want you to send to processor 1 in MPI com world. If we had another communicator, that physical same processor could have a different number, a different label associated with it. He could be 2 in my com world rather than MPI com world. Okay? So you have to specify that. Now, if you don't know how big your message is, there's a function, I don't know if I talked about this one. I forgot. There's also like a status in here. If we don't know how big our message is going to be, we can use the probe function. And we give it, I forget what it takes. I know it ends up taking a status, okay? What that does, what MPI probe does, is it basically you're asking, have I been sent any messages? Okay, and if you have, then it's going to fill out the status object. At which point then you can say, okay, I want to, we need an integer. We'll call this message size. And then you MPI get count, which takes the status, and then the data type, and then the message size. And I think I'm getting this right, and you're going to have to double check all this, okay? But I think I've got the right idea. And then we can do a resize of our vector to the message size, and we can do the actual receive. Like that. Okay, so the probe just basically gets information about the message. The receive actually gets the data from the message.
Don't you have to declare, I know this is just rough, but don't you have to declare your status somewhere?
Yeah, so it'd be up here somewhere. Just like that. Okay.
Wouldn't it have to be the same size as the array that you're sending? Or no?
Would it have to be the same size?
Doesn't status
Oh,
just hold if
I
it's
guess
sent
not.
everything or not?
I guess not, because you're only doing one send, so never mind.
You send the whole thing at once, right?
But-
Versus each little piece of the array.
Oh, yes. Yes.
I guess I'm just, so what does get count do? It gets the count of what?
Okay, so get count. MPI deals with bytes, okay? It doesn't deal with types. And so...
So you tell it MPI double, and that tells you how big each of the messages are.
Right, so an MPI double would be 8 bytes.
Right.
And so the status, so
Divides message size by 8, or divides the...
divides the number of bytes by 8 to give you the message size. Yeah. So we don't know the size of the message, so we probe and say, I need to know how big the message is. And then you get the count of that message into message size. I mean, if we used MPI character, that's 1 byte, and so we'd get the number of bytes that the message is. But since we're dealing with doubles, we want to use MPI double.
Okay, so I have another question. So what, when you say MPI probe and then status, what is that returning?
So what probe does is it waits until a message comes.
Okay.
So that is blocking. And then it sets the status to all of the information about that message.
Okay.
Does that make sense?
Kinda.
Kinda. So every message has a metadata, is what they call it. It's data that describes the data
Okay.
of the actual message. Okay, and that's things like your message size, who it came from, the tag, and other fun things like that we generally don't have to deal with. Okay?
Okay.
So if we want to know but MPI probe doesn't actually receive the actual data. It only receives the metadata, the information about the message. And it stores that into status. At which point we can then extract the information about that message using the get count function.
Okay.
Then we can use that to allocate a buffer to the correct size so we can actually receive the data.
Okay. So is there other get functions? You can get other things?
Actually, there aren't. I talked about this a couple days ago, last week.
Oh, this wasn't-
If we did, the status actually has two parts to it. I think that's them. So we could see out this, and it would tell us where the message came from, and then the tag of that message. However, because of the whole byte problem, there is no MPI size. Because MPI deals with bytes, not types. And so it has to convert for us from the bytes to the type. And so we use the function MPI get count to get the count of the message.
Okay.
And so when we resize our vector, we allocate some space for it, and we can actually receive the message.
Sorry, I have all sorts of questions, but couldn't you just say C resize and then the size of B?
No.
Why not?
Because I have written a very bad program here. Okay? You have to realize this program is being run on processor 0 and processor 1. They don't know anything about each other.
Okay.
And so in this case, we do not know how much data is being sent from processor 0.
Well, aren't both B and C allocated on both processors?
This is why I say I wrote a bad program.
Oh, sorry.
It's not realistic.
It's not realistic. Yes.
Okay. Sorry.
So anyway, in general, you're not going to know.
Okay.
If you structure your program correctly, you will. Now let me show you a bad way to receive your data. Well, you can be. Do you want to be? All right. So the bad way to receive your data is to have this is the bad way. What's wrong with this?
Well, you're receiving 100.
But what's the size of D?
0.
It's 0.
1.
It's 0.
Oh, it's 0?
Yeah. Hello. Because we haven't allocated any space in our vector. Okay. Another bad way to do this is like this. What's wrong with this?
Not allocated.
Again, it's not allocated. Okay, you have to allocate space, otherwise you're going to run into memory problems. You have to have somewhere to put it. So, anyway, that's the easiest way I know of in C++ to send and receive arrays of data, is using the standard vector. Okay? Alrighty, well, that's everything I wanted to go over. We're 5-6 minutes over, so email me if you have any questions, and we'll see you tomorrow.